speaking with Professor Neal Nathanson of the Department of Microbiology and Dean of Global Health Programs at the University of Pennsylvania. Thanks for talking with me today, Neal.
My pleasure.
These series of chats are part of our virology textbook, and our chat will be part of one of the chapters on viral pathogenesis.
Right.
And one of the first things I'd like to do to get going is to find out a little bit about where you were born and raised and educated.
Right. So I was born quite close to where the interview is being done here in Boston, namely in Cambridge. And as we were just saying, in those days it was much easier to get into college and medical school and so forth. So I went to the local places, namely Harvard College and Harvard Medical School. And in fact, I was more or less unconscious about it. Somebody else made all the arrangements, and but that's just how it turned out.
So you went through college with the idea of being a doctor? Is that how it worked?
Well, actually, when I was in college, I did an undergraduate thesis with a fellow named George Wald, who subsequently, in fact, got a Nobel Prize for really the biochemistry of vision. And I did a project in Woods Hole, one of those summer projects, and that was a lot of fun. And what it involved was actually just finding out what accounted for the change in color of a lobster. When you boil a lobster, it starts out sort of greenish, and then it turns red when you boil it. And my job was to take the shell off the lobster, extract the hypothetical pigment in the shell, and then figure out using cytometers and so forth what happened when you heated that. And it turned out to be a protein with a prosthetic group. And when you heated it, they separated, and the prosthetic group was orange in color, and then when you cooled it down, the resonance changed, the color changed. Anyway, that got me interested in science and the fun of doing science, really.
And then in those days, medical school was one way to pursue science?
Yeah, I think so. There were certainly people in my class who, in medical school, who went on and did scientific careers. And in fact, this was before there was an MD, PhD program. If there had been, I probably would have been in that program. In fact, I did think about applying to the PhD program in biochemistry at Harvard when I graduated, but that came after the medical school. And when I got into medical school, the look on my parents' face telegraphed a very simple message. You've got to do that, you know, my son, the doctor. At any rate, so that was the route I went. But I always had an interest in the research side of medicine. Yeah.
So after medical school, I presume you did an internship and residency?
Yeah, and again, that was the conventional. I sort of went along with the flow. That was the conventional kind of thing. And in those days, before there was an MD, PhD program, although the University of Chicago, interestingly enough, had already established one, but this was before the federal government had such a program. The standard thing, if you were interested in research and gone through medical school, was to do a postdoctoral fellowship. And that's where you learned your laboratory skills rather than enrolling in a formal PhD program. So actually what happened, Vinny, what happened was I started as a resident at the University of Chicago, did that for a year, and then in my second year, there was a doctor's draft. So, in one of those sort of life-changing events. And so I got a call, and my draft board, interesting enough, was the Cambridge Draft Board. And there was a lot of town-gown friction, and they rarely got their hands on a Harvard graduate who fell within their catchment area. At any rate, they told me in a month I had to report as a buck private if I didn't do something. So anyway, to make a longer story short, I ended up as a quote-unquote yellow beret, but in this case at CDC, the Centers for Disease Control in Atlanta, and that really sort of was a career-changing kind of experience because it happened when I arrived. It was just before the announcement of polio, of the Salk vaccine success. There was this enormous field trial. And right after that, something called the Cutter incident occurred. And I was the only person at that time who was sort of unassigned. So I was told to work on this Cutter incident This was out of Atlanta, but it was, of course, a national thing. And that got me interested in epidemiology. But then a fellow named David Bodian, who was invited down to talk about the pathogenesis of polio, because polio was on the front page of the New York Times almost every day for about 8 weeks because of this Cutter incident. That's back in the spring of 1955. And at any rate, Dave Bodian came down. He gave a couple of lectures about the pathogenesis of polio, which was his particular expertise. And I thought, this is what I want to do. It was sort of an eye-opening kind of thing. But in those days, everything was very informal. I wrote him a note. He said, fine, I'll get some money from the National Foundation for Infantile Paralysis, which was a major funding source. And so in July of 1957, I ended up at Hopkins to do a postdoctoral fellowship in his lab.
And what did you work on?
Well, actually, it was interesting. One of the aspects in the epidemiology was that the kids who got paralyzed from Cutter vaccine, which was this defective vaccine that had live virus, their initial paralysis almost always, and the worst paralysis, occurred in the arm or leg that they had been injected with a vaccine. So if they had been injected in the deltoid, their left arm or right arm, depending, would be first paralyzed, or in the buttocks and their leg. And the project that I was working on, so it was a training project, was to figure out how that happened and what made that particular sort of twist in the pathogenesis happen. We never really did get a definitive answer. We could reproduce the disease in monkeys, which were the experimental animal, but we really couldn't regularly produce the localization. So it's still one of those open-ended questions. But that really got me interested in the whole area of pathogenesis. So I did really research training for 3 or 4 years with Dave Bodian at Hopkins, and then I went over to the School of Public Health, where I spent 15 years at Hopkins.
And you had, did you have a laboratory of your own?
Yeah. In those days, things were sort of informal, and there was a major laboratory program within the epidemiology department, although there was a sort of microbiology or pathobiology department in the School of Public Health, but other departments also had laboratory programs.
So by this time you had become infatuated with viruses, I guess, and that's what you worked on.
And particularly with neurovirology and the pathogenesis of viruses, you know, the interface between here's the virus and all its properties, which, you know, you have spent your career on, and yet they cause different diseases, fast or slow, and what are all the parameters that are involved that determines one virus with one outcome, another virus with a different outcome, I mean, to put it in the simplest way. You know.
So one of the model viruses in our book is called LCMV, which you, I believe, worked on in your laboratory.
Yeah. I worked on many animal models rather than somebody like Bernie Fields, who just focused on one animal model. And LCMV was interesting because it was the prototype of a virus, as you well know, where the disease was caused by the immune response to the virus and not by the virus per se. And then that became a prototype. So LCMV, which is an obscure rhinovirus, really, of mice, has become an amazing model for a whole variety of immunological phenomena. And actually, there have been several Nobel Prizes associated with research on LCMV. It's a sort of an artificial model, but interesting. And so the work we did with that was, again, an animal model where if you used an immunosuppressive drug, you could change a lethal infection into a benign persistent infection.
Right.
And then you could reproduce the disease by adoptive immunization with lymphocytes from an immunized animal.
Right, showing it was immunopathology.
Yes,
right.
and reproduce the immunopathology,
So having spent so many years working on polio, at least your early years, and I think later you worked on vaccine-associated polio
and
as
I've
well.
always I haven't really worked in the laboratory on polio for a long, long time, but I've sort of followed it along, partly from an epidemiological and partly from a pathogenesis point of view.
So I don't know if you're still following it, but we are almost at the eradication port. I wonder if you have any thoughts about whether you think that will ever work.
Well, yeah, the polio eradication, which gets into the newspapers quite frequently, has now become really an exercise in civil unrest or international geopolitics, because the few countries, as you know, Nigeria, Afghanistan, Pakistan, which have never really gotten rid of wild polio virus. The reasons have been the vaccine is perfectly effective, but with all the civil unrest in those particular areas or parts of those countries, they have not been able to achieve a high enough level of immunization. So there has been an argument whether one should, meanwhile, across the world, of course, the polio immunization program has been very successful. So my guesstimate was that there were, before there was any vaccine in the 1950s, maybe 1 million paralytic cases a year around the world. That's been reduced to 1,000 to 2,000. And so the two schools of thought are, one, just let's leave it go at 1,000 to 2,000, and the other, push all the way to complete eradication. The problem, but this is my opinion, and it's quite controversial. The problem is those few epicenters where wild virus continues to circulate and has never been eliminated turn out to be seeds that then get transmitted to Syria, to Israel, to the Horn of Africa, to a whole variety of countries. And over the last 20 years, Nigeria, the virus in Nigeria, has seeded almost every country in Africa. So in a way, if you're interested, there's no distinction in my mind between control and eradication, because if you don't eradicate these epicenters, you clearly aren't going to be able to control these outbreaks that are happening, and every day you pick up the paper and the virus is spread to another area. So, but I think what's very unclear is whether we'll ever succeed. What's going on in northern Nigeria right now in terms of the girls who were abducted by this terrorist organization is, that's the kind of situation where polio immunization, forget it.
Of course.
Sort of situation.
It's hard. The vaccines are quite good, but
oh yeah, this is a failure to use the vaccine, not the failure of the vaccine.
So let's finish your career. You spent 15 years at Hopkins,
right?
And then what did you do after that?
So at that point, actually, Penn was looking for a new chair of microbiology. And for a variety of reasons, I thought the kind of research I was interested in could be better done in a medical school than a school of public health. And so I had an opportunity to apply, or was asked to apply, to come to Penn to chair the microbiology department. So in fact, I picked that up and moved the family from Baltimore to Philadelphia.
And you spent many years there. You're still there.
Right.
And you built a very substantial and successful department.
Well, we did, and it's interesting, and this is true. I don't know about the details at Columbia, but I think it's true of many institutions. One of the things that's very difficult to change in an academic institution is the sort of rigid structure of schools and departments. And yet, at least in microbiology, immunology, at Penn and elsewhere, there were people in many departments, as well as in the clinical departments and clinical service, who were doing either virology or immunology. So Penn at that time, this is about 30 years ago actually, moved to a system of what they call graduate groups, which were superordinate across all departments. So rather than change department structure, you could set up a microbiology graduate group, and people with appropriate interest and qualifications, whether they were in a hospital, in the dental school, the veterinary school, the medical school, the Wistar Institute, could all come together. So we made our department into what we called the Department Without Walls. And that was very effective because we multiplied the number of virologists who would come to a weekly seminar meeting from maybe, a dozen to 3 or 4 dozen. So, and of course, all sorts of good things came from that arrangement.
Well, in my view, Penn is still one of the few places in the country where there are many virologists, and I blame that on you.
Well, I'm not sure. What I did was give them all a home, regardless of whether they were, primarily in a hospital or in a dental school and so forth. And so that worked very well, but it was to everybody's benefit.
Yeah. Now, during this time, I think you were also an advisor to the president on AIDS. Is that correct?
Well,
the so-called czar of AIDS. Is that right?
What happened, actually, the way it started was Harold Varmus, when he came to NIH, that was just at the time when the new antivirals for HIV were coming out. But the idea was, and still an unrealized dream, was to make a preventive vaccine, because that's been the story, as you know, with most viruses, that the most effective way is to prevent rather than treat. And Harold actually turned to David Baltimore to create a little informal ad hoc advisory committee called the Baltimore Committee that went on for about 10 years or so. And I was a member of that committee. Well, David, of course, had worked on polio, as you know, for a long time. And at any rate, through that connection, I guess I was one of about a dozen members of this group. At any rate, that led to my eventually going to NIH and becoming the director of the Office of AIDS Research, which is also an unusual construct within NIH devoted to a single disease. Granted, it was sort of the plague of the century. At any rate, I did run that. So we were involved in directing AIDS research dollars, partly to basic science, partly to epidemiology and prevention, and also to vaccine development.
Okay, so you had built a department of microbiology. You continued research in your lab. You were this AIDS czar, as I call it. You also wrote a textbook on viral pathogenesis.
Right.
How do you balance these institutional commitments versus your own science?
Well, I sort of backed into these things, and so rather than, I've had a sort of, decentralized career rather than focus on one thing. And it was more or less by chance. I mean, I got interested in epidemiology, and then I spent all this time in the School of Public Health. And the reason I was acceptable to the Department of Epidemiology was, on the side, I taught an introductory course in infectious disease epidemiology, and also I was the editor of the American Journal of Epidemiology. And that sort of paid my dues as far as being an epi department. So then they let me free, as long as I could find the money, to run a research lab, doing issues or projects in viral pathogenesis.
It strikes me that what you said before about things being more informal then, it's very different now. You have to be focused. You really need to work on one thing. You don't just find money easily anymore.
Absolutely, absolutely. And I remember, this is maybe 40 years ago, I was at a meeting in Europe, ran into a fellow from Iceland. Now, Iceland had a sort of unknown sheep disease called Visna, turned out to be a lentivirus. So it was in the same category as HIV. But but those sheep developed a neurological disease, but nobody knew much about the pathogenesis. And the disease had certain elements in common with multiple sclerosis. So really off the top of my head, I wrote a grant with this fellow from Iceland, who was the director of a little institute called the Institute for Experimental Pathology. And we got a grant, I mean, it was sort of, and for 10 years we worked on that, and then Ashley Haas became involved, and he sort of took over that project and so forth. Although Ashley was at Minnesota, actually, he wasn't at Hopkins. But in those days, I think there was much more willingness to, put up some funding for new exploratory ideas, a little more risk-taking, and and people were much more willing. And there's been comments all over science, nature, et cetera, about this issue.
Yeah, I mean, I think being able to do science informally and at will is important for spontaneity, and somehow we're losing that.
Yeah, this curiosity-driven research and also risk-taking research. In fact, by happenstance, I had dinner last night with Stan Prusner, and I had, this is a long time ago, maybe 40 years ago, Stan had applied for a grant to the NIH, and it got thrown into the virology study section because nobody knew what scrapie and those diseases were all about, and they thought they were closer to viruses than anything else. And I remember, and I got assigned it because nobody else wanted to review this crazy grant from this crazy young neurologist at UCSF. But I was able to persuade the study section, it wasn't that much money, to give him a chance, which he's always been grateful for. But I think nowadays, the same grant would never have a chance of getting funded.
It's really unfortunate. Yeah. So what do you think, having worked in pathogenesis all your career, what do you think are some of the outstanding important questions that remain?
Well, I think that my sense, although I'm not into the technology, there have been so many new advances in technology, all of which can be applied. Partly there are incredible new developments in imaging, but there are also, of course, genomics and genome-wide association approaches and statistics, and and all of these new technologies, microarrays and so forth. So I think that probably pathogenesis is going to take on, let's say, a new chapter, a new life, using all these new approaches to re-explore models or problems which have been around for a long time.
So what about the observation that in people infected with polio, only 1 in 100 develop paralysis? Can you explain that?
No, well, not really, but I mean, one can speculate. I think one of the things that is peculiar about polio is that it's an innocuous enteric infection which doesn't cause any symptoms, as you know, in contrast to some enteroviruses that cause diarrhea, vomiting, and so forth. In order for the nervous system, either the spinal cord or the brain, to be infected, the virus has to undergo a viremia phase. And my guess is, and the experimental models sort of bear this out, that one of the gatekeepers that determines who might get paralyzed is whether or not there's a viremia, and also the titer of the viremia, which will determine, it's all a probabilistic thing, the probability of the virus invading the central nervous system. But again, that there's every answer leads to other questions, obviously. So nowadays one would speculate that that's partly genetic, and for instance, how fast your innate immune response is may make a difference as to, the level of viremia and so forth. Also, clearly, at least in polio, there are virulent and less virulent strains, and some of them are much more likely to cause high titer viremia and also paralysis. So there are a number of factors.
I view it as an accident because the CNS is a dead end for a virus, right? It can't spread to another person.
Right.
Whereas the gut replication is perfect.
Right. Right. So in fact, from the point of view of the virus, the fact that it paralyzes people is irrelevant. I mean, if you're going to put a personality onto a virus, its only purpose is to perpetuate its own genetic information.
Right. That's right.
And so the paralysis is really an irrelevant bystander effect from the point of view of the virus.
Irrelevant for the virus, but which drove humanity crazy for many years.
Absolutely, absolutely, exactly.
After your medical training, I meant to ask you this earlier, did you practice clinical medicine at all?
Well, no, I never did, because I sort of learned epidemiology along the way during the Cutter incident. And then, actually, it's interesting, when I went to Hopkins, some of my original classmates from medical school were there in various departments who were trying to do both things, that is, keep one foot in the clinical and one in the research. And I decided that you couldn't do both at the same time and do them, at least I couldn't do them well. And those people had a struggle, in fact. And there have been relatively few people who have maintained, I think, leading research and also become really competent clinicians at the same time. And nowadays, I think it's, at least at Penn, they've sort of set up tracks that recognize this, and either you're basically primarily a researcher or primarily a clinician. There are very few people who really do both in a high level of competence.
So you must have known both Jonas Salk and Albert Sabin.
Yes.
What
yes.
were their scientific personalities like?
Well, Salk was, just let me talk about Jonas Salk first. Odd because really his polio vaccine was, well, Albert Sabin called it kitchen chemistry, but it was very down-to-earth, practical, and it was perfectly competent science, but laboratory part of it was also quite simple, and he did a lot of course, experimental work in human volunteers to determine whether the immune response was adequate and so forth. On the other hand, Jonas Salk, you know, after the success of the Salk vaccine, underwent almost an incredible personality change, ended up as the original director, I guess, of the Salk Institute. Mm-hmm. His personal life also underwent major transformation, and he became sort of a biophilosopher. It was very strange, but his real strength, I think, was very down-to-earth, almost practical engineering applied science. Sabin, on the other hand, was more of a basic virologist, and although once he got involved with the commitment to make an attenuated virus vaccine, he became very focused on that. But if you look at Sabin's early history, he really did a lot of very interesting virology that was quite basic. In fact, I don't know if you're aware of this, John Enders got a Nobel Prize in, I think it was 1953, for work he'd done in 1949, showing you can grow polio in a variety of normal human tissues. Sabin actually did the same experiment 10 years before, and it's published in Proc Soc, a tiny little paper. But the mistake he made, I mean, I don't know if you'd call it a mistake. The misfortune he had was to use a neuroadapted strain, so it wouldn't go in normal human tissues. So that's a sort of irony. But Sabin was doing a lot of very interesting stuff. He was at the Rockefeller for a fairly long time.
Yeah.
So he was much more of a general virologist, and I think more of a deep thinker when it came to virology. But on the other hand, the minute that the two vaccines became competitive, they both became, well, to put it nicely, advocates for their own product.
Sure.
And, you know, and that sort of distorted their personalities. Well, they were both hard-driving folks who wanted the recognition.
Yeah. It's interesting, though, that so we used the Salk vaccine until 1961, we switched to Sabin, and then in 2000 we went back to the Salk.
Right.
And now WHO would like eventually to switch globally to Salk vaccine.
Right. So it turns out that, of course, both Salk and Sabin were correct in the sense that each vaccine had its own strengths and its own limitations. Mm-hmm. And one of the things about Dave Bodian, because he was my mentor at the time, is he would never take sides because he understood, if you looked at it just as a scientific issue, that each had its strengths, that each had its weaknesses. Clearly, Sabin vaccine, which is now the oral vaccine, the main vaccine that's used globally, can produce its own problems because it easily reverts to a virulent. So one has to really get rid of that in addition to wild virus. I think the world agrees. The problem is, can you convert the poor countries, really, to put it bluntly, from Sabin to Salk vaccine?
I think some new formulation and delivery methods are needed.
Yes, that's certainly possible. And there certainly are, rather than having to use a syringe and needle, there are a variety of things that you can apply to the skin and so forth that will go through the skin.
Right.
And also, of course, the cost of manufacturing Salk vaccine has always been greater than Sabin vaccine.
So this year, 2014, is the 100th birth anniversary of Jonas Salk.
Oh, really?
And there's a celebration in NYU in October, which I think is when the day is.
I see.
And you might be contacted to participate.
Right. No, I didn't realize that.
Yeah, it's just in the planning stages.
Right.
Should be quite
Well,
interesting.
they both need recognition. They both made it. And actually, one of the morals is that two vaccines in a way are better than one. I mean, at least in this case.
Yeah.
It's one of the, I guess, the only case I know where there are two vaccines, each one of which has its important position from a global public health point of view.
Right. So looking back on all the things you've done, and some of which we've touched on here, is there any one thing you've done in your career that you would say had the most impact to the field?
Well, you know, in a way, that's something you should ask other people, not me. I mean,
Well, you're here now, so
right,
I'll ask you.
Right. Well, you know, the pulling together all these different issues in pathogenesis, I think that's useful in a way, having skipped around different models and so forth. That's been useful. Also, I really have gotten very much interested in the interface between all the research and doing something about health inequities around the world, particularly in developing countries. And I got sort of cornered by Penn. That's what I'm doing now, which is running a global health program for medical students at Penn. But that's really, in a way, one of the big residual problems in health on a global basis, is doing something about the health issues in poor countries.
So Neal, if you hadn't been a scientist, what else would you have done?
Yeah, well, it's interesting, because some people might be vague about that, but I know exactly what I would have done. I would have been an architect.
Ah.
Yeah, I love architecture, and I happen to have a new partner as of a couple of years ago who lives in Cambridge, and she's into architecture, and that was one of the things that brought us together.
And what kind of buildings would you design?
Well, I think they would certainly be in the modern tradition. I'm not sure I'd have ended up as a Frank Gehry, but you know, certainly something new and exploratory. And again, I think the technology there has really, as it has in much of science, has really driven all sorts of opportunities in architecture which simply didn't exist 50 years ago. You know, both in terms of what you can construct and also how you can design it.
Right, materials have changed a great deal.
Right, and the way you can, you know, because some of these Gehry and other buildings, I mean, to make all the pieces that have to be molded into different shapes would have been impossible before the era of computers and computer-driven machines and all the rest.
Nevertheless, the Romans did pretty well.
Oh yeah, well yes, and in fact, I'm an enthusiast for, you know, Palladio, which really came out of Greek and Roman architecture, and has been adopted in a very effective way by a number of architects. Right. Yeah.
So a lot of individuals who read this book and listen to our discussion may be thinking about careers in science.
Right.
So what kind of advice can you give them?
Well, my first comment, and of course what I'm going to give you are mainly platitudes, which everybody will give you, but since you ask, I would say, I think the first issue is, as quoting Shakespeare, to thine own self be true. So if you have an experience, particularly an experience doing, at least in the life sciences, doing experimental work, which is, I think, where people really make the decisions for them or not for them. And if that excites you, you should pursue it in spite of what right now, hopefully temporarily, are the obstacles in terms of funding and so forth. So, you know, I think that's the most important thing. The idea of working on Wall Street when you'd really rather be doing experiments in the lab, even though Wall Street may, you know, have its advantages, I think that's most unfortunate. And so that would be, I think the first thing. Obviously, getting the best training you can is part of it, and you know, and again, having the intellectual and background equipment, which means, you know, learning the modern technologies, and finally, I think collaboration, because nowadays, even if you could live to be 100, you couldn't master all the relevant technologies out there. So you have to learn to be able to collaborate. You know, and there's this old, I think, mistaken idea, this myth that, you know, that to be a successful doctor, you have to be very good at interacting. To be a successful scientist, you can be a nerd. I think it actually is the reverse. It's much easier to deal with patients in a stereotyped way if you're not very good at interactions, and much harder to run a lab where everybody gets along and people aren't cutting each other's throats and so forth.
Right.
So I think, those skills are important.
How important is finding the right mentor?
I think that's critical. The right mentor and also the right niche, as you were commenting, something that, you really develop a passion for within the life sciences, whether it's neuroscience or virology or immunology, whatever it may be.
I've been speaking with Professor Neal Nathanson of the University of Pennsylvania. Thanks so much for chatting with me today.
It's been a great pleasure.